Okay, welcome back. Hope you guys had a nice, relaxing spring break. From packet 2, I think most of you guys showed me page 9 through 12. I know some of us were not here on Friday, so tomorrow I'll be checking the rest of packet 2. So if you haven't shown me 9 through 12, I'll check that, and then I'll also check pages 13 through 16. I'll send out a reminder this afternoon. So today we're going to start packet 3. And really, we're just working through FRQs. This should be more familiar since a lot of this is from second semester. So today we're just going to work through pages 1 and 2. Whatever, we should finish it. If we don't finish it, then you'll do the rest for homework. So tomorrow I'm going to check pages 1 and 2 from packet 3, and then the final pages of your packet 2. Okay. So no assessments this week. But we're going to eventually get to our quiz reviews starting Thursday, Friday. So the quiz will be Riemann self-differential equations, 2 FRQs, and we'll have Friday and Monday to do full reviews. We're kind of hitting them now a little bit, but our quiz will be next Tuesday. Okay. And this will be another 50-point FRQ quiz grade with this packet 3 homework accounting for the other 50 points. I have your quiz graded, but I'm waiting for to check your homework tomorrow, and I hope to have your grades in by tomorrow, Wednesday. Okay. After that, we have we're going to start our multiple choice test review, and this is packet 4, and the final week before May, the final week of April will be EOC days, EOC week. So all the days will be cut short, but Monday and Thursday are a little bit longer, like 30-35 minutes. So we'll take a 8 question multiple choice derivative test on Monday, and then 8 question integral topics, spring semester topics, multiple choice test on Thursday. Okay. And again, that will lead us into May. So your AP exam week starts that first week of May. So I know students will be in and out, but we'll be working through some of the FRQs from the FRQ packets. Okay. Does anyone not have this packet? Okay. So this FRQ packet will be due, ideally, I would like for you guys to finish before the AP exam on the 8th, but I'm not going to require it. So as long as you turn this in to me by the end of the school year, or before senior, if you're senior, turn it before senior grades are due, and then you'll be able to earn a 100-point quiz grade. There's another assessment that I haven't given out to you, and that is the assessment 5, but I'm going to call it packet 6 here. These are multiple choice tests and also some problems from the AP classroom. So I'll give this to you hopefully later this week. But again, these 2 are just packets that are not gonna, I just want you guys to work through them, complete it. I'll give you guys the key. Just have to, I just want to get you guys exposed to a lot of different problems before the AP exam. Right, but this will be, if you just complete it, you get an automatic 100-point quiz grades. Okay. Any questions? Okay. So, oh, and then again, this next quiz, you will get a formula sheet, but then the test, the multiple choice test, I'll tell you which form to choose to focus on. You should be focusing on the first semester derivative rules, and then second semester integral rules. But you will not. You will have to memorize those rules. They will not be available for you to use on the test. Okay. All right, so these are particle motion formulas. We'll reference them once we need them. But let's look at number 1 here. A car travels on a straight track during this time interval between 0 and 60 seconds. The car's velocity, v, is measured in feet per second. Acceleration is feet per second per second. They're both continuous functions. The table above shows selected values of these functions. So let's just kind of get a feel for what's going on here. The car information is notated at these specific time intervals. So at 0 second, velocity is -20, acceleration is 1 feet per second squared. Okay, and at 15 seconds, 25 seconds, all the way to 60 seconds. Now, looking at these negatives and positives, can you verbalize what's going on in terms of this direction of motion? Is changing at 50, right? I mean, maybe it changes somewhere between, but because we don't know the exact times, but it seems like he's gonna at least change direction at least once, right? But then here, assuming that there's no sudden change, which direction is this car moving in? Yeah, well, it's straight track, so yeah, we assume left and right, but we just say opposite direction, right? So opposite direction, moving to the left. We can also consider that. So it's moving left, but then we know for sure it's going to be stopping at 50 seconds, and we know for sure that it's going to change direction and move to the right at least once. Okay, so part A says using appropriate units, explain the meaning of the definite integral from 30 to 60 of the absolute value of v of t in terms of the car's motion. Okay. Approximate using a trapezoid approximation with 3 subintervals determined by the table. So what do you think this absolute value of v of t integral is going to tell us that's different than without the absolute value? Okay. Without the absolute value would just be what? Displacement, yeah. So without the absolute value, we're just going to know, where he is in relation to where he started, right? But with the absolute value, that tells us total what? Total distance, right? So with total distance, we don't care where he ends up, we're just going to keep track of every motion that the car makes and count that as positive distance. Okay, so part A. Part A, we know that we can say that integral from 30 to 60 of absolute value v of t is the total distance traveled between 30 and 60 seconds. But now we're going to actually find that approximation of total distance using trapezoid approximation. So here's the area formula for trapezoid is 1/2 width, height 1 plus height 2. We can do width over 2, or you can pull that 1/2 out in front. Either is fine. They're the same thing, whichever version you want to use. Now, because we're doing total distance, what's going to happen with all these negative values here? Yeah, we want to consider everything as positive. Even the negative, even though we're moving to the left or moving the negative direction, we still want to count that. We want to count the region between the graph and the x-axis as positive. So even though the graph may look something like this, we still want to treat all of this as positive area. We know area between the velocity and the x-axis is going to indicate the distance, right? But if we keep it negative and positive, then we'll do displacement. But if we keep everything as positive, then we know the total distance. Okay. So between 30 and 60, this goes back to Riemann sums. We have to pull the width from the difference of each of the subintervals for under time. So between 30 and 35 is one subinterval. From 35 to 50 is one subinterval. From 50 to 60 is one subinterval. And if we subtract that distance between 35 and 30, that's the width of the first trapezoid. Between 35 and 50 is a width of 15. Between 50 and 60 is a width of 10. So for our first trapezoid, we'll do 1/2 times 5. And then what's h1 plus h2? 14 plus 10, yeah. And the second trapezoid is 1/2 times 15. And then 10 plus 0. And the third trapezoid, 1/2 10, 0 plus 10. Now we know that velocity is meters per second. You know that you're multiplying this by time. So meters per second times time will give us meters. Sorry, feet per second times time will give us feet. So that's why this integral process will change that velocity unit of measure to a distance unit of measure. Okay, part C. Part B, sorry. Using approximate units, explain the meaning of depth integral from 0 to 30 of AFT in terms of the car's motion. Find the exact value of the integral from 0 to 30 of AFT. So, are we good with part A? So we know that if I take the antiderivative of acceleration, what's that going to turn into? Velocity, right? So this is really a rearranging of first theorem. So first theorem, I thought I had it here. Yeah. Displacement velocity. If I take the antiderivative of acceleration, turns to the velocity, and I can plug in my upper and lower bound. Right. So I know that when I take the antiderivative of acceleration is v of b minus v of a, and that's just the difference of velocity, right? The change in velocity between point A and B. And that's what information is going to give us in return. Okay. AFT turns into velocity. We plug in our upper bound and then lower bound. So this feels like it makes more sense, right? It feels more concrete. We know whatever this this car's velocity is at 30 seconds, and whatever the object's velocity is at 0 seconds, we subtract those two and we just figure out the difference between those two velocities. Okay, so V of 30 we can pull from the table. V of 0 we can pull from the table as well. Sorry. So we know 0 seconds, he's moving at -20 feet per second, and then at 30 seconds, he's -14. So if we subtract those two, we see that basically it's telling us the car's change in velocity between 0 and 30 seconds, which is 6 feet per second. Okay, good so far, A and B. Part C, between 0 and 60, can we guarantee a time t when the velocity is exactly -5? So let's look at the velocity table here. Can I guarantee that my velocity is going to hit -5 somewhere along this interval? Okay. And why is that? Yes, within this interval, right? We know that somewhere between -10 and 0, it's got to hit -5 somewhere in between because we're dealing with continuous functions here. It's not going to be able to skip over a number. So there's no calculus involved here, right? We can just tell by a table this continuous function, and if my target is between two other numbers, then it's got to reach that number in between. So that's IVT. That's intermediate value theorem. So the way that there's different ways that you can write IVT, but I think that it's always a little bit cumbersome to write out the description. But this is, I think, the way that is most efficient because you can get all the information out to the graders to let them know that you're applying IVT. It's the fact that you know that your target of -5 is between -10 and 0, and -10 and 0 is coming from 35 and 50. So IVT guarantees a time between 35 and 50 such that my V of t is equal to -5. Now for D, can we guarantee a times between 0 and 60 where the acceleration is equal to 0? So looking at my acceleration, can I guarantee that's going to hit 0? Not by looking at acceleration, right? So we can't use IVT because we don't have the data for IVT to tell us, because I mean, it's possible that it could reach 0, but based off these numbers, it's also possible that it could just be floating above 0 and never hit 0. So IVT is not going to do the trick for us. You know what we could rely on then to help us guarantee acceleration to 0 somewhere between? Say it again? Yeah, how can our velocity guarantee us acceleration to 0? Okay, so let's do this here. Let's say this is 15, 25, 30, 35, 50, 60. Let me just graph the velocity and just see what we could do here. Let's say this was -10. This is a very rough sketch here. So let's say at 0, our velocity is -20. At 15 seconds is -30. At 25 is -20. -14. -10. 0 and 10. So this is the picture of our velocity graph. Now, acceleration is the what of velocity? Derivative was another word for derivative. slope, right? So it's asking, is there a place where acceleration is zero, or basically, is there a place where the slope of velocity is equal to zero? Can we guarantee a slope of zero somewhere along this graph? Okay, and why is that? What theorem can we use? If my endpoints have the same y value, my slope is guaranteed to be zero somewhere between. What theorem is that? Rolle's theorem, right? So I like that they paired up C and D together because we can kind of see that clear distinction between IVT and Rolle's, right? IVT is just looking at the exact table set of values and looking to see, can does it make sense for the graph to hit that point somewhere between? So that feels easier, right? You don't have to worry about looking at a different function than the one you're working with. But with Rolle's theorem, this is where calculus comes in because we don't have to look at the acceleration. We can look at the velocity, right? If we know that acceleration is the slope of velocity, as long as my velocity is able to reach the same y value, then I know that in between it's got to be able to go down and come back up, or go up and come back down. And that process is going to create a slope zero. So I think hopefully that answers a lot of the questions that students have in terms of, how do I know when to use IVT? How do I know when to use Rolle's? You kind of have to look at the data and obviously you want to probably start with IVT first. It feels easier. You just look at the table of values. Say, can I look at these values and guarantee that the value I'm looking for is going to be reached? If not, then maybe I can look at the function above it and look at it from the slope perspective. Okay, number 2. Sorry, wrong one. Okay, temperature of water in the tub is modeled by strictly increasing twice differentiable function. So we know the graph is always increasing. We only have a limited set of values here. Oh, sorry. We only have a limited set of values here, but we know that it's not going to dip suddenly between these values. It's going to always rise like what we see in this table. And twice differentiable just means that it's a smooth curve. There's not going to be any sharp turns or any holes. Okay, W of T is measured in degrees Fahrenheit, and T is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time t equals 0. Values of the temperature of the water is for the first 20 minutes are given in the table above. So at 0 minutes, temperature is measured at 55 degrees, and then over the course of the 20 minutes, it slowly rises. So part A says use the data in the table to estimate W prime of 12. Show the computations that lead to your answer using correct units. Interpret the meaning of your answer in the context of this problem. So we don't have a function to find the derivative, so we can't find the exact value of W prime of 12, but what could we use to help us get to do an estimation of it? Yeah, find the slope, right? Because we know that W prime of 12 is a derivative. An estimation of the derivative is basically the slope. And we're kind of forced into using these two order pairs because these are the ones, because we know the closest order pairs to 12 is 9 and 15. So it's not going to be perfect, but based off the data, that's the best we have. So we either do the change in temperature or change in time. So what's the units going to be? Yeah, degrees Fahrenheit per minute. And what does it mean in the context of this problem? Yeah, so we know that on the 12th minutes, the temperature of the water is changing at a rate of some value degrees Fahrenheit per minute. We get a positive value from that slope. So we know that on the 12th minute, the water temperature is increasing at around 1 degree Fahrenheit per minute at that 12th minute. Part B, use the data in the table to evaluate the depth integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning of the depth integral from 0 to 20 W prime in the context of this problem. So let's use first theorem. I think it makes it a little bit easier to interpret what's going on here. What's the antiderivative of W prime? And then we can plug in what? The 20 and the 0, right? So we know that W prime, integral of W prime is just W of 20 minus W of 0, right? And what is this information going to tell us? Change in temperature between the 0 and the 20th minute. So just how much the temperature change between, if you're comparing between 0 and 20 minutes. So sometimes this feels a little bit abstract, right? This doesn't feel as easy to interpret, but if you can use first theorem, then this feels a lot easier to verbalize and to make sense of. So the 20th minute, the temperature of the water is 71 degrees. At 0 minutes, temperature of water is 55 degrees. So we know that over the course of that 20 minutes, the temperature increased from 16 increased to 16 degrees. Okay, for part C, between 0 and 20 minutes, the average temperature of the water in the tub is given by this integral formula. So this is average value theorem here. So that's why it's average temperature here. So let me remind you, average value theorem. So it's basically taking all the temperatures, and dividing it by 20. Right? So if we accumulate all the temperatures divided by 20, then we can get that average temperature. It says use left Riemann sum with 4 subintervals to approximate the average temperature. Does this approximation overestimate or underestimate the average temperature of the does this approximation overestimate or underestimate the actual average temperature of the water over these 20 minutes? So let's not worry about that 1 over 20, but we do not want to forget about that 1 over 20. Let's just focus on finding that area using left Riemann sums. So it says use 4 subintervals, and we're going to do a left Riemann sums. So from 0 to 20, we can create our 4 subintervals, right? 0 to 4 is one subinterval, 4 to 9, 9 to 15, and 15 to 20. And then we just have to pick out the height, the width and the height for each rectangle. So for the first rectangle, width is 4. What's the height of my first rectangle? 55, because I want to use the left Riemann sum, right? So within each subinterval, I'm always going to have a choice. I'm going to choose the left one or the right one. They're telling us left Riemann sum, so we're going to choose 55. How about for the second rectangle? Yep, the width is 5, the height is 57.1. Third rectangle, width is 6, height is 61.8. Fourth rectangle, width of 5, height is 67.9. So make sure that you're comfortable picking out the width and the height for the tables. I don't think it's difficult, but you know, it's also easy to make a mistake if you're misinterpreting the numbers wrong. Right? I see some students, they add these numbers together. They do 4 plus 9, make it 13, or 15 plus 20 is 35. And so we want to find the width, right? We're not going to add them. We're going to subtract the minutes to get that width. So that's going to give us our integral, but we still have to remember that we have to divide all that by 20, right? Because if you add all this up, it doesn't make sense that the average temperature is like 300 degrees, right? That doesn't make sense. You got to take that accumulation of temperature, you got to divide it by 20. This makes more sense, right? 60 degrees, that feels about right because we're going from 55 to 71, so somewhere between 60.79 feels like a average temperature that makes sense. So this is the left Riemann sum. We know the graph is always increasing. So if your graph is always increasing and you're doing a left Riemann sum, will your approximation be overestimation or underestimation? Under, right? And this is something that you don't want to have to memorize. If you just sketch the graph and you sketch a rectangle, you should be able to convince yourself whether your rectangles are clearly above the curve or clearly below the curve. So this is all below the curve. This is going to be an underestimation of the actual temperature, of the actual average temperature. Okay, part D. Between 20 and 25 minutes, the function W that models the water temperature has a first derivative given by W prime. Based on this model, what is the temperature of the water at 25th minute? So we know a formula that gives us the rates that the temperature is changing at any moment in time. But I want to actually find the temperature at the 25th minute. So any idea what formula that we can use to help us get there? So we have this, right? We have this final equals initial plus displacement. Well, so in this case, if I want to find my final temperature, I have my initial temperature, which is that 20th minute. By 20th minute, I know is 71 degrees, and then we can just figure out that difference, that change in temperature to get to that 25th minute using that formula. Okay, so if I want to find the temperature at the 25th minute, I can just start at the temperature of the 20th minute and then figure out the rest using integral, using antiderivative. Because we know the integral from a to b of w prime will give us that change in temperature between the 20th and 25th minute. And if I can find that change in temperature, I can add that to my anchor, my 20th minute temperature, and I can figure out that if I know the change, if I know what I have, I can add those together to figure out where I end up. Any questions here? Okay, I know it's been a while, but I've been meaning to give back your chapter 7 area volume test. And I'll give that. It's in a great book already, but I'll get that back to you with the remaining time. But I was trying to figure out why students were having so much trouble with cross section on the test. And I think I figured out. I just want to kind of point that out, see if this makes sense. With disk and washer method, right? You know that you're always drawing a radius that is perpendicular to your axis of revolution, right? You have your axis, whatever your axis is, you know that your radius or your length is always perpendicular to it. But with cross section, so for instance, okay, with cross section, if a problem says parallel to the x-axis, that is the direction of your base length. Okay, you're not going to do anything different from whatever direction they tell you. So parallel to the x-axis is this direction, right? Parallel to the x-axis is this direction. So you're going to hold your base length in that direction. And I figured out why students were always doing the opposite of what they see here. And I think it's because you guys have been doing that with washer and disk method, right? Every axis they tell you, you're always doing something that is perpendicular to it. But here with your axis, we're not rotating around anything. So if it's a cross section problem, whatever direction they tell you is the direction of your base length. Okay, it's the orientation of your base length. You don't have to do a change like with disk and washer. Does that make sense? I feel like that's where I see a lot of students trying to change that direction because that's what you normally would do if it was washer or disk method. And then another common mistake that I saw was like whenever I say rotating around the x-axis or rotating around x equals 3, that's a vertical line. Some of us were drawing a horizontal line as a rotation that just threw everything off because then your radius is a different direction. So if it's x equals 3, that's not the horizontal line. That's a vertical line. So that means your radius is going to be horizontal. Yeah, so I think it's always that first step, right? If you can get past that first step, then everything else makes more sense. Then mistakes that happen are fewer and fewer. Okay, so I'm going to send out a reminder this afternoon that I'll be checking the remaining pages of your packet. If you didn't show me 9 through 12, I want to see that, as well as page 13 through 16, and then also show me page 1 and 2 that we just completed with worksheet 3, or packet 3. All right, come and get your phones.